Okay, so let's start. Yesterday we ended up at the where we stopped was the binomial and then the beta distribution. We looked at how we use the likelihood function for binomial data and what the prior distribution of that would be. So here we have our binomial model. So we have the likelihood function for the binomial, and then we use the beta as the prior distribution for the parameters. And then we ended up with our posterior mean, which is alpha over alpha plus beta, and then we have our posterior variance to be here. So today we are going to look at a Poisson data. So you all know a Poisson data. How will you know that this data has a Poisson distribution, apart from just looking at the curve? How will you know that the data has a Poisson distribution, apart from just looking at the curve?
If it is an event of occurrence, just one event.
I mean Poisson distribution. When do we say data has a Poisson distribution? What is the nature of data that has Poisson distribution? They are in numbers, isn't it? You are counting number of people, number of items, number of females, number of males. So when you record numbers, okay, whole numbers, then we say the data has a Poisson distribution. So here we are saying that let's assume that we have a data that has a Poisson distribution, and then you know the Poisson distribution is written as this. So the rate is lambda, and then the data is y. So we are saying that the distribution of the data given lambda is going to be equal to e to the power lambda, lambda to the power x, and then we have x factorial. This is the distribution that we have for the Poisson data. I will rectify this. I think this value, this should have been, yeah, so that is the distribution, yeah. So y equals to this thing. So this is the probability of the data given certain values of x. Now, the gamma distribution is the conjugate prior. So the conjugate prior, so I'm saying, because remember we talked of conjugate priors yesterday. So for conjugate prior, so what that means, if we take the gamma distribution and multiply it by the Poisson distribution, the resulting posterior distribution is also going to be gamma distribution. Now, using this gamma distribution, we should be able to find the mean for the gamma distribution and also the variance for the gamma distribution. You know how to do these things under estimation. So this can be written as integral. So it can be beta to the power alpha, all that over gamma of alpha. Then we can take integral of this, and then we have this component. Now, if we want to find the expectation of this function, so the expectation of, I'm just reminding you of what you did under your estimations. So if you have this function and you want to find the expected value or the mean of the lambda, which is the rate, is going to be, let me just share the whiteboard and show you something here. Yeah, so this is the whiteboard. So if I want to find expectation of lambda, if I want to find expected value for lambda, then this is just simply going to be equals to, so I'm going to have the integral of lambda and then the likelihood function or the distribution of the data. then I'll differentiate with respect to lambda. This is what I'll have. The expected value of lambda is going to be integral lambda multiplied by the function. So that is the same thing. So the gamma function that we have there, so we are going to have lambda multiply that by the gamma function. So if we do that, if we do this, let's go back to the slide. Can you see the slides?
Yes, sir.
Yeah. So what that means is that here we are going to have integral of lambda multiplied by lambda to the power alpha minus 1 multiplied by e to the power beta minus beta times alpha. So when you do that, then you solve this. At the end, you are going to get your expected value to be alpha over beta. Then to find the variance, remember the variance is defined as the expected value for x squared or lambda square minus the mean square. So that means you are left with finding expected value for the mean square. So the expected value for lambda square, you do that in this equation, and then you get the function, then you substitute it into the formula. You have done these things under estimation. We shouldn't be wasting our time here again. So you have the variance for the lambda, and then you have the mean for the lambda. So the mean for the gamma distribution is alpha over beta. The variance for the gamma distribution is alpha over beta squared. So with different values of alpha and beta, these are the kind of curves that we are going to have. So here, what are we interested in? This is what we already know under our estimations. I hope you guys have done these things under estimations.
So we can't remember.
Hey, you can't
Not that
remember.
we didn't do into detail.
All right. So when we have a tutorial, I'll take you through to know how to get the mean. Like in our face-to-face meeting, we'll find time to, I mean, solve these things, take the integral and then solve for alpha, solve for the lambda, the mean, and then the variance. When we meet in class face-to-face, I will do that for you.
All right, sir.
So that's just 1 hour. The time is not enough for the face-to-face, and then I don't have the writing part, so kind of very difficult for me to illustrate here. So let's see, when we meet our face-to-face meeting and there is time, we'll be able to illustrate this. We are interested in finding the posterior mean and then the posterior variance. How do we find that? We know that the posterior, which is the lambda given the data, is equal to the product of the likelihood function, which is here, multiplied by that of the gamma distribution. So if we do that, so here are just more examples or illustrations on that. So just go back to the next slide. If you take this function, just look at this component, just look at this part only. Just look at this part, take this part and multiply by this part. You see that you have e to the power lambda, and also you have e to the power minus beta times lambda. So what that means is that that part, if you multiply them, you are going to get e to the power lambda, open brackets, 1 minus beta. Then you take lambda to the power x, multiply by lambda to the power alpha minus 1. This is going to give you alpha and lambda to the power x plus alpha minus 1. So when you do this, in the end, you are going to get something like this. Can you see that? So that means your lambda given the xi, that is the data, that is going to be proportional to lambda to the power xi plus alpha minus 1. And then here we are going to have alpha lambda multiplied by n plus beta. So you can see that n plus beta is, so you can see that, remember the gamma distribution is distributed as, those of you who will join and unmute yourself, please, I'm going to remove you from the group. Everyone is muted upon entry, so I don't see why you should unmute yourself and be making noise in the background. If I find that, I will just remove you, because when you are talking, the symbol is, I can easily detect that you are the one talking. Please desist from that. You only unmute yourself when you want to talk. Please, I don't want to remove anyone, because that is not good. So here, so if we multiply this part by this part, that is what we are going to get here. See, remember the likelihood function for the Poisson, which is here. We are going to have e to the power. So that means if we take the likelihood function of this, we are going to have this times, so because we are going to take a product of this component here. And if we take the product of this component, then we are going to have e to the power n lambda, and then lambda to the power summation of xi. That is what we are going to have. Then if we go here, so what that means, our lambda is going to be summation of the xi, that is the data, plus alpha minus 1. So our alpha is now this part, summation of the data plus alpha. So our alpha is now here. And then our beta is now n plus beta. So our lambda, that is the posterior mean or the posterior distribution for lambda, given the data, is going to be equals to gamma. So it's going to have a gamma distribution with alpha, summation of xi plus alpha, and then the beta is now n plus beta. And this is the posterior for the gamma distribution. So you multiply a gamma prior by the Poisson distribution, the end result, that is the end result of the posterior distribution is going to be the gamma distribution. So our posterior,
Okay, sir.
yeah, Ben.
So please, in that case, can we also write it in by applying the property of the property of summation that says that summation I is equal to 1 to n, xi is equal to xn plus a n plus b. Can we do that like
Which one are you talking
the
about?
summation I mean the posterior.
You said we can write which one, like
the final answer.
You said we can write it as
the first as nxi plus
you mean
a
this one,
and n plus, yes, the summation side.
Yeah, you are yeah. So this the
By applying the property.
You said we can write it as
nxi plus a.
You said we should write it.
Is it also correct? nxi.
Why nxi?
Yes, which still means summation xi.
Why are you saying some? Why are you saying nxi?
N multiplying xi.
Yeah. So why are you
saying
x? Go on.
Yes, summation xi I ranging from 1 to n is the same as nx, n multiplying x, according to the property.
Yeah, are they the same values?
Yes, please.
I mean the x values, are they the same?
Yes, please.
How do you know?
Because in this case, we are assuming that there is a random, x, i's are random variables ranging from 1 to n.
Then I'm asking you, are they the same? Let's assume that you are saying that 2
So if
plus
you say,
3, example, for instance, 2 plus 3 plus 5 plus 7, is that the same thing as n times that? Huh? Ben, if the x's are not the same, how can you use n to multiply?
no, in that,
You only do that when the x's are the same. If you have 2 plus 2 plus 2 plus 2, it's the same thing as the number of the 2's times the 2. But here, do you know the value of x?
xi.
Do you know the value of xi? If you have n plus n plus n plus n plus n plus n, 5 of them, that will be 5 times n, isn't it? If you have 2
Yes,
plus
sir.
2, if you have 2 plus 2 plus 2 plus 2 plus 2, that is n2s. So now, if you have 2 plus
Yes,
2, 3 of them, that is just going to be 3 times 2. You only do that when you have the same numbers, not when you don't even know their numbers. Is that clear?
Okay, sir. Well understood. Yes, sir.
All right, let's move on to the next slide. So here we are now talking. So now let's go back. So we now know that our gamma, our alpha is equals to summation of xi plus alpha, and then our beta is equals to n plus beta. So we go back into this slide. We return to this slide. So that means our alpha is now summation of xi plus alpha, and our beta is now n plus beta. So we are going to substitute that into this and then substitute that into this one. So if you go back here, so the posterior mean is going to be equals to the alpha, which is now summation of xi plus alpha. Divide that by the posterior beta, which is n plus beta. And this can be simplified as what we have here. So you divide the summation of xi by the denominator, which is this. Then you take the alpha and divide by n plus beta. And you can simplify that further. And now, as you simplify that further, so you can see that this can be simplified as n over n plus beta multiplied by this. So this, you can see that this is just mean n plus beta over n plus beta that. So you can see that you can express this in this form. And the data, so we are saying that the data get weighted more heavily as n approaches infinity. I remove the other n here, it shouldn't be there. As n approaches infinity. So as your n becomes very large, that means your data is going to be weighted more heavily because you are going to take n multiplied by the data. And that is what the expression is saying here. Otherwise, our posterior mean is just this guy here. So if you want the posterior variance, yes, Ben or Isaac. Yeah, Isaac, go on.
Yes, sir.
Yeah.
Please, what is the relation between Poisson and gamma? Why are we considering the gamma Poisson? Why not?
Did you attend the fair?
Any other distribution?
Did you attend yesterday's lecture?
Yes, please.
So what did we say about the prior distributions for these data distributions? What did we say about these prior distributions? We are listening. Can you talk, please? What did we say about these prior distributions that we are using? Yesterday, we talked of the normal prior, we talked of the gamma prior, we talked of the beta prior, and so forth. We are listening. So, Isaac. Yes.
Please, I'm coming. Sir, please, please continue for now.
Clarify for us why you say we should continue so that we all know why you are saying that.
The guy is giving us.
Hello?
Yes, sir.
Why are you saying?
Sir, please, I'm now going through the slides.
But you said we should continue. We want to get clarification before we move on. We want to be sure that you understood what we are doing before we move to the next slide. So you have raised an issue. Let's clarify that before we move on. Do you now understand why we are using gamma and then versus do you now understand why under the Poisson distribution we are using gamma prior?
Sir, please, if somebody can help me, any of our friends.
Help you in terms of what? What help do you need? That's why we are here. Raise your problem and let's solve the problem together. If you don't help us, there's no way we can help you. What is your problem? Isaac, we are listening.
Sir, all I was asking was why the gamma Poisson distribution.
And
I want to know why.
Did you attend the first lecture we had via Zoom yesterday?
Yes, sir.
Did you see the table where we have the various distributions and the associated conjugate priors or not? This table here, do you have this table in your slides or not?
Yes, sir. Yes, sir.
So what did we say here? Can you see the slide?
When the conjugates.
Come again.
You were saying when the posterior is in the same family as the proud, we have the conjugacy. The conjugacy.
Mm-hmm. And you want to violate that, or do you want to advise us to violate that?
No, sir.
So why are you asking that? Why are we using gamma with Poisson? If you want to ask us to stop using that, you can advise us and tell us your reason. Because I don't know why we have shown the table here and we are using them as our examples to illustrate our work, and then you are having problem with that. So if you have issues with that, tell us where you have issues so that we stop using gamma against the Poisson distribution.
Sir, please, I'm sorry, I didn't get a table at first. That's why I was asking for the relation. But now I've understood, sir. Thank you, sir.
All right, so let's move on. So always, some of the distribution, you just have their conjugate prior, which you just use them. Some of them, you can use none if you are not too sure about the distribution of the parameters. So you can use maybe a uniform prior distribution, or you can use a vague prior distribution. So depending on the information that you have, but we are saying that these distributions, they have their priors, and we call them conjugate priors. And what did we say about conjugate priors? We said that for the conjugate priors, if you take them and multiply by the distribution, the resulting posterior is going to be the same as that of the prior. And we demonstrated that using the normal distribution. So we take the conjugate prior for the normal distribution, which is a normal distribution, and multiply by the data likelihood, which is a normal distribution. And we ended up with a distribution which was posterior distribution, which was the same as that of the gamma distribution, the normal distribution for the prior. Then we did that also for binomial. So we picked beta distribution for the parameters, multiply that by the data distribution, which is binomial. And then the end result of the posterior was also a beta distribution. And now we are illustrating with the gamma distribution. So our conjugate prior for gamma distribution here is gamma. For Poisson distribution here is gamma. And we have seen the gamma distribution. We pick the gamma distribution, which is the prior, and then multiply that by the Poisson distribution. And we are able to get our resulting posterior to also have the gamma. And we know that from there, we found that our gamma distribution, the alpha is summation of x plus alpha divided by the beta, which is now n plus beta. So we just do algebra up to this point, and that is that. So you can also do for the variance. So the variance is alpha over beta squared. So what that means is that you are going to have this over n plus beta squared, because the variance is defined as alpha. So our alpha now is summation of xi plus alpha. And then our beta now is n plus beta. So we're going to have n plus beta square as the variance for the posterior distribution. So more example here, you can look at this. So we are saying that if our data x1 up to xn, these are the data points, are identically and independent distributed as Poisson. So we have our Poisson. So we have the IID, independent and identically distributed with Poisson as lambda. Then the gamma, which is the prior for the beta, is a conjugate prior, because if we multiply the gamma by the Poisson, the resulting posterior is going to be gamma. That's why we say it's a conjugate prior. Gamma is a conjugate prior. So gamma distribution for the parameter lambda is a conjugate prior. So here we have the likelihood function for the Poisson. So we take the product on the likelihood function. So this is going to be e to the power minus lambda. So because we'll be having lambda plus lambda plus lambda minus lambda minus lambda. So the end result is going to be minus n times lambda, which is this one here. And here we are going to have xi plus xi plus xi plus xi. So lambda is equal to xi plus xi plus xi. So that will give us lambda to the power summation of xi's. And then we have the product here. This is our prior. So if we multiply this by that, then we'll get this result, which we have seen in the previous slide. So you can look at this one. And then our posterior mean for the lambda is going to be x plus alpha, which we have seen before, and then n plus beta. This is the algebra that we just did. So the same thing. Here we have the exponential and then the gamma. So we have the exponential distribution. So suppose that we have values of x to depend on theta to be exponentially distributed, and that we use a gamma prior distribution. So our theta, we assume that the theta has a gamma prior, a gamma distribution. So that is the prior distribution for theta is gamma, defined by alpha and beta. So our gamma distribution, as usual, is this one. And then we need to find the posterior. So the posterior is going to be the gamma distribution for the parameter multiplied by the exponential distribution. So here, the first part here you are seeing is the gamma distribution for the parameters. Our parameter now is the theta. So you have to note that it's no longer lambda. So you can replace theta with lambda, is the same thing. So we use theta as our parameter here, and that is equal to alpha minus 1 e to the power beta. So if we replace this with lambda, is the same as what we've seen before. And then we take the likelihood function of the exponential distribution of the data, and that is going to give us this. So if we expand this, so if we take the product of this component here, so we're going to have theta times theta times theta times theta. So that will give us theta to the power n. Theta to the power n. And then we take e to the power theta xi. So we're going to have e to the power xi times e to the power xi in that order. So we'll end up having theta summation xi. So it's going to be e to the power theta times summation of xi. So if we do that, this is what we are going to get. So here we are going to have theta to the power n. So if we multiply that by this one, we are going to have theta to the power alpha plus n minus 1. And then we take this one, which is e to the power minus theta summation of xi. So if we take the e and then this one together, then we are going to add the exponent. So we are going to have e to the power minus theta, which is...
Please, your sound is off.
Yes, we'll stop. You don't have lecture, so don't worry, we will stop soon. I have to finish this. Or you have another lecture.
The class is 5 to 6.
Yeah, is it not up
It's
to 6?
5 to 6. Yes, it's 5 to 6.
Yeah, that is the, we are ending. So I just want to finish up with this because I can't
Okay.
stand in the middle. So
Okay.
we are going to have e to the power beta plus n. So here we are just saying that the summation of x is the same. You can write it as this. Remember this one. So remember this is just summation of x. So summation of x, you see this component here. If I write that, you know, this x bar is the same as summation of x over n. So the n will just cancel this n, leaving the summation of x. So it's the same thing. So you can write it as n times the x bar, or you just write the summation of x, is the same thing. And then we have our theta here. So here you can see that. Here you can see that.
Oh, sir.
Yes.
I think the previous question I asked, no, that is what is appearing here.
No. What you are saying was completely different. You know what you have just done here? We have done nothing. Just replace the x bar. Just replace the x bar by summation over x, summation of x over n and c. Is it not the same thing? So it's just the same thing as summation of x. Unlike when you are saying x1 plus x2 plus x3 plus x4. That cannot be x nx. Are you getting? When you add x1 plus x2 plus x3, that cannot be nxi.
Okay, sir.
Unless the x1, x2 are the same values.
Okay.
So here, what we are simply writing is here, we haven't done anything. No, it's just the same thing as summation xi. Because the x bar is summation xi over n. So if you have summation xi over n, the over n will cancel the n that is here, leaving your xi.
And exactly.
So they are not
exactly.
So this is what we have as our posterior. So that means our theta, the posterior distribution for theta is going to be gamma, but alpha is now going to be alpha plus n, and then our beta is going to be beta plus n So if you don't want trouble, you just write your summation xi and be free. And that is that. So this is where we are going to end our lecture. And we are also ending our lecture on one variable. The next time we'll meet, we'll look at, so here you can see that we are only focusing on one parameter. So when we meet in our next lecture, we are going to look at how do we apply the Bayesian paradigm to regression models. If we have
We can't hear you.
Sir, we can't hear anything. Sir, we can't hear you.
that, can you hear me?
Yes, please.
Yes,
We can
please.
we can now hear you.
So I'm saying
The
that next
past
semester
minutes we
we'll look
couldn't
at
hear you.
how the next semester we'll look at how we use software to estimate these parameters from these models. And in our
Sir,
next,
so we are done for this semester.
no.
Next,
In our
Done
next
for
meeting, we are going to look at that. You see, we want to apply, we have to, this is just the beginning, or kind of, I mean, it's kind of surface, because we are just illustrating with a single variable. In our next lecture, we will look at if we have a regression model with several parameters, how do we do that under the Bayesian paradigm? So we'll look at logistic regression model that is describing the binomial data, and then we'll assume a prior distribution for the gamma, a prior distribution for the parameter where we'll use gamma, and then see what is going to be our posterior mean and then variance from that. And then we'll look at the Poisson regression model, and then the associated prior, and then what will be the posterior. And that will be, so we are going to deal with the three situations: Poisson data, binomial data, and normal data. So once we are able to do this, see how the formulations are done, how to obtain our posterior means and variance from these models, then we end the course. Next semester is going to be simulations. We just take each of these models and see how we implement them using software. So if there is question, please ask. Otherwise, we end the lecture here.
Yes, sir, please, we want to know if you have recorded. Okay, you have recorded.
Oh yeah, when I come to office on Sunday, I will share the slides. Tomorrow I will not be in office.
So you can upload it on the YouTube.
Yeah, I'll upload them on the YouTube.
Yes, if you could send us the link to the YouTube too.
Yeah, I'll upload them on Sunday and then share the link with you.
you have a YouTube.
Okay, sir.
Yes, sir, has a YouTube account.
You are not reading your messages on your group, eh?
-5.
The YouTube link is there. You can go there and then listen to the videos. When you go there, even the other classes, you see that I've even uploaded for the other classes that I'm lecturing. So you don't need to download it. You can watch it on your phone.
Yes,
Okay.
That's all.
And we subscribe.
thank you, sir.
Yeah, so I'll meet you on my.
Please, you have to do where and subscribe to when you go to when you get to.
Yeah.
Sir, please, we will show
Okay,
inside the
sir.
videos.
Come again.
Are we also showing inside the video?
Oh yes, all of you are showing inside the video. So if
Yeah,
you
so
are,
when you subscribe to the video, sir, 10 marks.
so those of you who will just be lying on your bed anyhow, The video will capture you like that.
That's it.
So when you
I
are
hope you subscribe to the
everything is
video.
recorded, so it will be on YouTube. So when you are coming for these lectures, you make sure that you make sure that your environment is neat and yourself is properly dressed.
Yes, sir.
Yes, yes.
People
We do
will
that.
see you. Yeah, so that's fine. All right.
Okay,
So
sir.
if there's
Brother,
no
is there any mark for subscription?
come again.
When you subscribe to the YouTube, say 10 marks.
You want man?
Okay, thank you,
There is
sir.
no
Bye
mark for
bye.
subscription.
Please, can you also follow you on Instagram?
No,
Oh,
no.
master. Instagram,
Like,
yeah,
Okay, so we'll meet next week.
Okay, sir. Nice having you around.
Okay,
Bye bye.
bye.
Uh,